Okay. And so I would like to talk about the moduli space of, well, these pairs x delta. So I will sort of slowly tell you what x delta is and sort of start with sort of knowing very, very little. So certainly this, so x will be projective. Now, in the general setting, it does not have to be normal. Like in a stable curve doesn't have to be normal. It can have some singularities, but for most of what I say, you can pretend that is normal. So sort of all the problems that we have to deal with appear in the normal case. And this delta will be just a divisor, sum of ai di a divisor. Okay? Now, and so this x essentially has some log canonical singularities. So this log canonical. And again, for quite a lot that I'm sort of telling you sort of what you need to know for now, the main examples, or sort of the classical examples, singularities like C and mod a finite group, okay? Now you see the consequence of this, that the canonical class of this will not be Cartier because the group messes it up, but some multiple will be Cartier. So we have to deal with cases when some singularities or some divisors, they're not Cartier, but some multiple of them are Cartier. And now the other example, that if you start with, say, a smooth projective variety inside some projective space, and you look at the cone over it, so that sits inside sort of affine n+1 space, so this is the cone, then what can I say about the singularity at the vertex? Okay? And so there are two things that are easy to compute, that the canonical class of Z, this is Q Cartier, so some multiple of it Cartier. This holds if and only if the canonical class of Z arithmetic linearly equivalent to some multiple of the hyperplane class. Okay? And then the other thing that you will need, that the singularity is log canonical if and only if this alpha is less than or equals 0. And no, that's why it's Q. So this is just Q. So then it should mean if you multiply both sides by some sufficiently divisible number, then you get a linear equivalence. Okay? And so that means that you can have the cones over Fano varieties, they are sort of nicer, and also the cones over Calabi-Yau's when alpha equals 0. Okay, now, and so then what's the standard way of constructing moduli? Say if you want to construct the moduli of, say, smooth projective curves, then so the first step is to, and so if you have a smooth projective curve, okay, well then sort of first you pick some multiple of the canonical class, and this embeds C into some large dimensional space. And so then you say that I look at something like the Hilbert scheme there, and you say there will be an open subset of it that parameterizes exactly these smooth projective curves, and then so this embedding is not unique, it's unique up to automorphism, so then you have to take the quotients by the automorphisms. Okay? Now, so then we will follow the same procedure here, So we are dealing with a case that generalizes this case. So we will have always the assumption that kx plus delta is ample. Okay, so this is exactly the analog of the canonical class. And for at least the first half of the talk, you can just pretend that delta is 0. So if you don't like delta, then just saying that delta is 0. Now, and so that means that some multiple of it is actually a Cartier divisor, and it's ample. So then that means that we will then be able to realize this as sitting inside some projective space, and then we take the quotient by the automorphism group. Now, but you see, even if you set delta equals 0, if you just look at something like the Hilbert scheme, you would like to say that the varieties that we like, they form an open subset, like in the curve case, being smoothness is open. And so, well, yeah, so being a smooth curve is open, and then you have to make sure that it's embedded by the canonical. Okay, so now here the situation is more complicated. Let's see, for instance, this example. So this will sit, it's a determinantal form, the equation, maybe that's the easiest. Okay. x1 plus tx4, x2 plus sx5, and then here x3. Okay, so if I say that the rank of this is less than or equal 1, this defines some variety script S that sits inside. So it's P5 cross A2. So the x coordinates are here, and the s and the t coordinates are there. So I view this as a family of varieties, happen to be, I believe, threefolds. Okay, so let's see what happens here for the various values of s and t. Well, okay, so the generic case is when s and t are both non-zero. Well, then I can pretend that this is just x4 and this is just x5. And now then here this describes, I believe, the Zegra embedding of P1 cross P2 into P5. So this is smooth. As far as the singularity is concerned, this is nice. Okay? Now, then the other extreme case is when s and t, they are both 0, okay? Now, if s and t are both 0, then these two are wiped out. And you see here, so two of the coordinates vanished, and you see here the equation of the degree 3 rational normal curve. And so it's the cone over the rational normal curve taking twice. And so as I told you, this says that this has the right kind of singularity. So this is log canonical if you know this is even KLT. Okay, so this is even slightly better. Okay, now what about the third case when either S or T is 0 but not both? So the situation is fairly symmetrical, and so then I think you get essentially x0, x1, x2. Maybe here I can pretend that this is x4, and then this will be x2 and x3. And maybe this is not sort of the most frequent form, but this is F1 embedded into P4. So it's a degree 3 surface, and I take the cone over it. And you see that here, the canonical class is not a multiple of the embedding class of O1. And so that means that here, I have something where the canonical class is not Q Cartier once I take the cone. Okay? And so this means that this being log canonical as singularity wise. Okay, so you might say that here the canonical class is not ample. You can easily fix it by taking something like a ramified double cover, ramify along a sufficiently high degree divisor. So that's that's okay. But you see that so here in families, this being log canonical is neither open nor closed condition. Okay? And so sort of there's one problem. Problem one, being log canonical is neither open nor closed. Okay. And so actually the main problem is the Q-Cartier condition. So it turns out that in general this Q-Cartier is not even a constructible condition. Okay. But at least in this example it is. But still you might say that it's hard to get a moduli out of something like this, yeah? When you have this large open set and only one point of the complement. And so you know, this sort of looks very bad for moduli purposes. And so now, one thing though you can recognize that maybe the origin is actually, it is different from the generic fiber, and indeed they should not be in the same family. Okay? And so why is it? So, okay, I think I didn't write down here, but if you compute the self-intersection of the canonical class, where it makes sense, examples 1 and 2, then you see you get different numbers. Okay? Well, and so if here I have A2, then it's log canonical here, and log canonical at the origin, but it's not log canonical along these lines, yeah? Yeah. And so this means that somehow our moduli problem, it should not be just flat families of varieties with canonical singularities. And so what is the problem? Well, you see, the problem is that if you are in a family of algebraic varieties, say, let's just write down a one parameter family, say a family over a smooth curve, and say the fibers are normal or something like that. Well, then what is a relatively Cartier divisor here? And if you have a divisor that's Cartier on every fiber, that does not imply that the divisor itself is Cartier. Okay, so that's the simplest example. But although, I mean, there is an example there, but maybe you can sort of see better that if you look at the quadric cones, they degenerate. So we start with the quadric cone, and then you degenerate to it as hyperboloid, and you take sort of here two parallel lines. Then maybe I can do it. Oh, okay. So you have two parallel lines, but this is clearly a Cartier divisor. And in the limit, you can arrange that you get two lines like this. That's also a Cartier divisor, where it is just cut with the hyperplane. But this is not a Cartier family. For instance, here the self-intersection is visibly 0, but here the self-intersection is actually 2. Yeah? Okay? So that means that you have to distinguish what is, fiber-wise Cartier and what is actual Le Cartier. And so then this leads to us that sort of what we have, what I usually call a stable family. So I have this X. Okay, now I don't know how to make a curly delta, but okay. Over S. And so now then the condition is that this Kx plus delta, so maybe here I should take the relative canonical class, that this should be Q Cartier. And so the claim is this is much stronger than it being just fiber-wise Q Cartier. This should be Q Cartier. Now, so we will actually say a few more words. What is a divisor actually, and how does this make sense? But okay. So then this takes us to the question. Well, let's say okay. Let's say theorem. So I think first I state it without delta because it's actually the clearer. So let's assume I have an f x to s. This is a flat and projective and normal fiber. Okay? And now, then, well, so what are the good families? So maybe here I define the functors. So if I have some t mapping to s, okay, then I get, so then f of t, which maps from x of t, which is just x cross st to t. And so then I say that this is a stable pullback. So this is stable if, well, there are two things happen, that the fibers here, they have log canonical singularities. So log canonical fibers. Actually, okay. So maybe, since I don't want to assume, let's say just locally stable here, I focus on the singularities. And plus, that if I write down the relative canonical class, this is Q Cartier. Okay? And so, now then, normally you would like to say that, for instance, for curves, that, a functor like this, the pullback of smooth family is representable by an open subset. Now, as that example there shows, this is not true here, but the claim is that there is a monomorphism S locally stable to St that represents this functor. Okay, representing this functor. And so that means in this example that I have here, the monomorphism will be, so I just have the origin, and then I take the disjoint union of it, or A2 minus the coordinate axis, so this mapping to A2. So if you work through in sort of these examples, then this is what you get. Now, today So you mean that S is a disjoint union of local? I mean, I don't understand what you mean by there exists a monomorphism. Yes, there's a monomorphism like this that represents this functor, and so that means that each time you have a morphism, and the pullback has this nice property, then in fact this T2S factors through uniquely like this. Okay, this holds if and only if, yes.
And what's the structure of the
Well, it's a quasi-finite monomorphism. I mean,
monomorphism?
Yes, monomorphism. It's an injective morphism, yes. 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 And it's, I mean, of course, your favorite examples are just, open subsets embedded, or closed subsets embedded. And I mean, essentially that happens here, yeah, except so we have to make sure that these are these joints. So the line that starts at the origin and goes off here, that is not allowed. Yeah, that's what I'm just doing here. But sort of there is a scheme that represents Zeno's disfunctor. Okay? And so that means that you know, I mean, in some applications of this, of course, this will be something like the Hilbert scheme of some large projective space, and then so this will be the universal family over it. Yes, I mean, so it's okay. It doesn't have to be normal, and then at least that means that I have to act the automorphism not on the Hilbert scheme, but on this one to construct actual moduli space. Now, so I would like to explain the proof of this today, sort of not in the general scheme setting, but only for semi-normal schemes. So in some sense, what I'm saying today, it will not construct the moduli space, only the semi-normalization or the normalization of the actual moduli space. So the problem is much easier in that case, but a lot of the interesting questions they come up. Okay, so actually, the hard first step is to.
So you said something at the beginning that I didn't understand.
Okay.
You said that the locus where it's not, where it is not canonical is not even constructible in general.
No. I hope I didn't say that. The locus where it's Q Cartier. Yes, the locus where it's Q Cartier is not constructible, and sort of I will in fact run into this problem.
Okay, and so here you.
So this definitely says that being log canonical is a constructible condition. Okay, this definitely implies if I add this quasi-finite. Okay, so let's see the first step is interesting, is to prove that being log canonical is a constructible condition. Okay, so then if I have some f x to s, then I look at sort of all s in s such that xs is log canonical, and I would like to prove that this is a constructible subset. Okay. Now, there's an easy way of doing this. So you know, I sort of may assume that S is irreducible. That's fine. I look at the generic point, and then see what happens there. Okay. So now I think at this point it becomes inevitable that I define log canonical actually. Okay. So where should I put it? Maybe this picture can go. And so let's assume that if I have a normal variety Z, when is this log canonical? I write down a resolution of singularities and assume that the exceptional divisor has only simple normal crossings. Okay? So then I can write, so maybe this is pi, the canonical class of Z prime. I can write it as a pullback of the canonical class of Z. And then plus the Jacobian formula gives me some corrections which involves the exceptional divisor. So these are exceptional. Okay? Now we all know that when Z is smooth, then these AIs are always positive. Okay? And then, so our important classes of singularities, they are all defined on how far are we from the AIs being positive. So the log canonical case is when the AIs are larger or equal minus 1. So log canonical if and only if AI larger or equal minus 1 for every time. Okay? Okay. Now then, let's see if I can show you here. So then I start with the generic fiber. Okay? So I have here the generic fiber. Okay? And then say, let's assume it's log canonical. And so maybe case 1, if it's log canonical. Well, okay, so then I can write down a resolution of singularities, x prime g, 2xg. And if I did this in the generic fiber, I can spread it out in some open set. Yeah? And then the exceptional divisors, they also just spread out, and the spreading out these coefficients, they do not change. And so if they were larger or equal minus 1 in the generic fiber, then on an open set where sort of everything stays a resolution with normal crossing divisor, I still have something that is log canonical. Okay. Now let's see the two. What happens if it's not log canonical? Well, so you see, as long as this formula makes sense, I'm in business. Because if it's not log canonical, well, that means, at least you first might think, that means that there is an AI that's less than minus 1, and by the same argument, then there is a Zariski open neighborhood where this AI less than minus 1 survives. Okay, now, but there is something that I did not emphasize enough, that, of course, this pullback doesn't always make sense. This pullback, this only makes sense if this KZ is, well, for starters, for Cartier, but if some multiple of it is Cartier, then I can define the pullback. Then I get rational numbers. I'm completely happy with rational numbers. So it's not LC, but KZ Q Cartier. Okay, so that's okay. And so then again the same argument works. But I am sort of stuck if it is if this is not Q Cartier, then I cannot do a pullback. And indeed, so here I come into this problem that being Q Cartier is not an open condition. So for instance, if you look at some, okay, so let's start with some, smooth curve of something sufficiently general, and embed it into some, well, PM may be something like 2 times the canonical class plus a degree 0 line bundles. So I let this vary, okay? And now then here I take a cone over it. And then if you look at it, then you see that the canonical class of that will be Q Cartier precisely when this L is a torsion in the Picard group, okay? So you see from here that being Q Cartier is not a constructible condition already in this very simple case. Now, luckily, this is not log canonical. So something happens for log canonical. And now let's see, well, maybe I can squeeze this argument a little more, okay? That maybe I can define this pullback in a slightly more general setting. Okay, so when can I define this pullback? Well, and so let us say that X is numerically numerically log canonical if, well, if I can do what? So this kz I can represent with a divisor, yeah? So if I have a divisor, so the birational transform of kz, so this is just the sometimes called the proper transform, the birational transform, plus sum of ai, ei. This is pi numerically trivial. And so that means it has zero intersection with every contracted curve. Okay? And so now you see that, so then if the generic fiber is numerically log canonical, then the same argument shows that the nearby fibers are also numerically log canonical. Okay? So now then what happens if it is not numerically log canonical? Okay, well, so how do I see that? Well, you see that, so I can view kz and the ei's as some linear functions on the relative cone of curves, sorry, maybe z prime over z to maybe q, okay, or r, or whatever they want. And it is numerically log canonical, but if and only if kz is a linear combination of the ei's. But if that's not the case generically, if they are linearly independent, then this is also an open condition. So that means that being numerically log canonical or not is a condition that I can spread out from the generic fiber to nearby fibers. This is exactly shows by this example that you see adding this L does not change the numerical condition. It does numerically nothing. And then so the claim is that when being Q Cartier behaves unexpectedly in the family is not constructible, then it's always because of the connected component of the Picard group. So numerically, it does not hurt us. Okay, so now we know that we have numerically log canonical, and now, well, so then you ask the usual suspects, and so that was my conjecture and proved by Haken and Shu that numerically log canonical is exactly the same as log canonical. Okay, so numerically LC equals LC. Okay, so the same thing. So you know, if you want to think about it, so you know, if you write down a chain of rational curves like this, yeah, then you see right away that its canonical class is numerically trivial. But it needs an argument that its canonical class is actually trivial. It's a non-trivial statement. It's sort of a deep statement. That, well, so maybe in this case it is not too deep. But there is something similar happens for any higher dimensional Calabi-Yau thing. That if it sort of looks like its canonical class is numerically trivial, then in fact it is linearly trivial. At some multiple of it is linearly trivial. Okay, so that means that then we can finish this argument by Noetherian induction. Okay. Now, in fact, we sort of get something stronger that we can write this locus as in fact the union of some SIs where the SIs are locally closed. Okay? And so if you look at the induced map xi over si, then these are locally stable families. So then indeed by our construction, the KSI over Si, they are Q Cartier. Okay? And so now comes the question of sort of how to decide how to assemble these SIs. Yeah? So for instance, I can have one S1 that's an open set, and then I can have something part of a boundary and maybe this point. So I can have sort of 3 of these. I have to decide somehow if I sort of have to glue these two together into a larger variety from the functor point of view, and whether this point always misbehaves or not. Okay? And now, so here actually there is a, so in fact, sort of how to assemble something out of constructible sets is mostly a question about what happens over DVRs. Okay? So we sort of need to understand how can it happen that something has Cartier fibers, but it is not Cartier. So let's think about this just a little bit, because that's another thing that we need to complete. Okay. So let's do this over, again, this is it's just a smooth curve. So it's 1 parameter family, flat, let's assume normal fibers. Something like that. Okay, and now let's assume that I have a divisor here, D, and then I assume that if I restrict it to any point, this is Cartier. Okay, so well, you sort of might ask what exactly I mean by this, okay? Because that's a key point. You see, so our divisors, when they come, they will not be Cartier. So this is something like a weight divisor, okay? And so now that means I can restrict it to a fiber. It's a 1 parameter family restrict. I get a weight divisor there, and then I can identify this with a divisor. But you see, this means, and so maybe there's a warning sign here, that if I look at the structure sheaf of that, this will be not the same as the structure sheaf of the restricted to the fiber, okay? Because there might be some embedded points coming up where it is not Cartier. And then similarly, maybe what is more interesting to us, if I look at this OD minus D, this sheaf, again I can restrict to the fiber. So how does it compare with OX minus DC? Well, there's a natural map like this, but again, this map will not be an isomorphism. Yeah. So, what's the point? So this is, by construction an S2 sheaf. So this satisfies Chaire condition S2, essentially. So the Hartog's theorem holds by chance. But so unless this satisfies Chaire condition S3, the restriction will not satisfy S2. Okay? But you see this all, so this satisfies S2, which means that the restriction is S1, so it means that this map is an injection. Okay? And so this means that if I then take now the Euler characteristic is, so if I look at chi on xc, OXC minus DC, and then let's twist it with something relatively ample. And now here, but this is flat over the base. This is just something like a smooth curve. So then here, this side, if I take the Euler characteristic, I can do it in the generic fiber. So OXG minus DG. Okay? And I know what? I know that this is always less than or equal. Well, sorry, I forgot to twist with M. So this is less than or equal for M sufficiently large. And equality holds if and only if this map is an isomorphism. Now, if this map is an isomorphism, then of course, and this DC is Cartier, then the local equation here leads to a local equation here, so then the family is relatively Cartier. So that means that I can see it as part of an upper semi-continuity statement. I can check whether a family is actually Cartier just by computing the Euler characteristics. And so now then how to deal with that constructible locus? Well, I have these sort of pieces of that constructible set. I just look at the pieces where this Euler characteristic is maximum. Yeah? And now then this says that that locus has to be closed. Okay? So then that will be one of my final pieces. I take it out of my space and I go down. I construct these. I construct this monomorphism. And so that means that in some sense this will be indexed by these Hilbert polynomials that I get here. Okay, so this much about this. Okay, now then, let's see. Yeah. Okay, now we bring in the deltas. Okay, and that's actually another substantial headache when the deltas come in. In fact, is the divisors that give us headache, sort of the most headache here. Okay. So again, let's look at an example. So this will be fairly similar to the previous one. So here I will have a cone, except here I take the cone over C4, the rational normal curve inside P4. Okay, so that sits inside P5. And so that's the degree 4 surface, and I think already Bertini knew the degree 4 surfaces inside P5. Now, but I'm interested here, that will be just P1 cross P1, but it's embedded not by O1, but by something like O1, comma 2. Okay, so this will be a sort of a general hyperplane class. And now here, what I want to take, see if you take the cone over it, well, it's not low canonical because the canonical class has degree -2 on both, whereas this is not symmetric. And so let's try to fix it by adding some delta. Normally you would just sort of add 1 with coefficient 1, but in a moment you will see instead what I do is I add these two components each with coefficient 1/2. So the delta will have these two divisors with coefficient 1/2. And now here I fix this problem. So if I take the cone over it, including the divisors will be the cone over it, that will be now log canonical. Now then what happens if I specialize it here? Well, the specialization will be just here, both of them with coefficient 1/2. Okay? Now, well, so what's the problem here? This is there's a perfect nice deformation, the kx plus delta. In fact, here 2 times it is in fact relatively Cartier. But you see that delta itself is not flat over the base. Okay? And so here there are 2 components, Euler characteristic 2 here, but here I have just Euler characteristic 1. So that means that although before, I could just say that I have just these flat families to start with as far as the base is concerned, I cannot do the same thing with delta. I cannot just say that, again, now let's look at the Hilbert scheme of divisors or something like that, because I have to include things that are not flat. And so the question is, what do I need to include delta? And so this is the question that has been, so it gave us a lot of trouble, in fact. And so here it is actually much easier if we work over a semi-normal or over a normal base. So maybe in the remaining 10 or so minutes, I would like to explain sort of what happens. What happens here that's nice. So, okay, so there is what is essentially the lemma of Gauss. I mean, maybe this is a more general form that if your S is something like normal, okay, and you compute the class group of X cross AN, then it's just isomorphic to the class group of X. Okay. Now, and so this is nice. Maybe sorry, there's supposed to be an S here. Okay. No. You see, of course, in general, we would like to have something stronger. So we would like to know whether something like this holds for sort of smooth morphisms. Yeah. So the product with AN. So what would be really nice that so if I have some say so maybe Y to S smooth, then what we really would like is that the class group of Y is isomorphic to the class group of S. But unfortunately, this is not true. So maybe as exercise, I leave you to find an integral domain such that the class group of R is trivial, but the class group of R, bracket T, is non-zero. Okay. So that's already when you go from just polynomials to power series, then things get messed up. Now, and so although this is not true, this really wants to be true. Okay. And so here's the theorem it's quite helpful, and at least I haven't seen this before, but it's sort of hard for me to believe that this was really not known. So if you know a reference to it, then please let me know. So let's assume that I have, so here S is normal, okay, and here I have a smooth morphism, okay, And let's take a divisor here. Yeah. Now, so then here the Gauss lemma essentially says that, of course, there are divisors that are just pulled back from the base, so they don't have to be Cartier, but sort of everything else is in fact Cartier. That's something trivial. And so let's assume something stronger. Assume that D does not contain any fiber, or maybe precisely any irreducible component of a fiber. Okay? So then the claim is that D is Cartier. Okay? And so over something like Z or over dVr, if this S is a dVr, then this is equivalent to Gauss's lemma. In general, it is stronger. I need to assume it does not contain any of the fibers. Over a higher dimensional base, that's a weaker condition. Yeah. And so this means this actually is very good news for us because we sort of really have this built in that I have these divisors that hang around. I really don't want them to contain a fiber. So that is not something I really want it to be a divisor in each fiber. So that means that the divisors that we get are automatically at least Cartier at the generic point. Okay? And so you see, I want to emphasize that although this morphism is smooth, because S is just normal, this Y can have sort of pretty bad singularities. Okay. So maybe let's see. I don't have much time, so let me just explain maybe why sort of something like this can be true, and I think as part of it I will do your homework. But I have bad experience with assigning homework to mathematicians with PhDs. They essentially never do it. So I can as well give the solution now. Yeah. So what can go wrong? Okay. So let's assume that this S is just a cone over a curve, say over an elliptic curve, okay? Now, then what are some interesting classes here? Well, the lines give interesting classes, yeah? And so the lines they give something that's very large in the Picard. In fact, they generate the local Picard group. And so now then what if I go to some higher dimensions, say I just take the product of this with something, okay? So then, well, so how can I get some interesting divisor here? Well, I mean, okay, I can get some non-interesting divisor. I can take a line and I can take the pre-image. Okay. But maybe what's more interesting, that I can just take lines, but I can vary the lines as I move up. Yeah. Now, and you see, that's why Gauss's lemma will hold. But as I vary the line, so that will give me a map of this fiber to pick 0 of this curve C. Now, Gauss's lemma says if it's A1, then these maps are just constant. Okay? So you can in fact sort of reformulate Gauss's lemma by saying that you have a normal singularity, then this local Picard group, whatever it should be, it does not have an A1 subgroup. Okay, but it can have some other subgroups. So, for instance, if F itself is this Picard, yeah, then of course there is identity map, and that means that there will be a line that goes up. But you see this construction, which in fact will give you the whole Picard group here. In the projective case, or if F is projective case, and these are precisely the new elements of the Picard group. But you see, this will be non-Q Cartier at sort of almost all points here. Yeah? So it means that the only way you can construct these new divisors, that they will be in fact not Q Cartier everywhere along that fiber. And in fact, this is the general picture. So now, of course, then how to get this? Well, if you work, say, over Q, then you know you can arrange that this has only one point, the origin, over Q. Yeah, and so the formal arc still maps there. So that's how you get this example, although it doesn't have any points. Okay. Oh, let's see. I think there's a lot more I wanted to say, but I think that yes. So maybe I just want to sort of state the sort of last statement that is very much like that. And so, okay, so that's theorem 2, how to deal with the boundary. Okay, so let's assume that I have f x to s. So this is flat, and here actually, well, it's a normal fiber, but in fact S2 fibers are okay. Okay, and then it's projective, and then let's assume I have D inside X, so it's a codimension 1 pure subscheme. Okay, and then so let's assume that this D does not contain any irreducible component of any fiber, so it's reasonable condition, and I need the strong condition. So then that this D is Cartier at generic points of ds for every S in S. You see, this is exactly what we got here. If you have a normal family, then the family is smooth at every generic point, so that means that this Cartier condition holds. But so once we are through that, we can be sort of more general. And then you can look at, again, a similar functor, but sort of then now, sorry, it's not written here, but no, it was written here. So then if you have this T anymorphism T to S, then you can look at, well, the pullback xt dt. And now I want to emphasize that, of course, this is not just the pullback of the subscheme, but I pull back the subscheme, and then I have to make sure that it becomes pure. I have to throw away the embedded points, okay? And so that this to T is so there's log canonical here, so that's the functor that I'm interested in, and again the claim is that this is representable by a quasi-finite monomorphism S log canonical to S. Okay, so then this is the way, and again sort of here the moment, so the proofs I showed you, this claims it only for semi-normal scheme. So So I'm sort of representing the functor at the moment only for semi-normal schemes. It needs different techniques for if you want to handle the scheme theory right, but it's okay. But it's different. Yeah. Thank you.